is the turning point. It's the critical point for this seminar series in terms of the number of participants. So maybe we should wait for a couple of minutes to
get out of the critical region.
Yes, otherwise the fluctuation would, yes, dramatic. So let us maybe wait for 1 or 2 minutes, and I will start introduce you to the audience. But by just by looking at the references, it seems Sören, you are working on this topic, this problem for more than 10 years. The first paper is around 2000.
Yeah, this is true. I mean, this is something, you know, that sort of started as a hobby a long time ago, right? But now we are doing more work on it in recent years. So.
So I think without further delay, let us start slowly. So today is our real pleasure to have Sören Schlichting from Universität of Bielefeld to give today's seminars. If you really attended the Zemanya Award ceremony 2 days ago in Quackmatter, you may know. I mean, it's not necessary to introduce Sören to you, but for the general audience, so let me begin with some of his biographic informations. So Sören was Sören was taking the undergraduate school at Darmstadt, and he graduated in 2009. After that, he took the master program between 2009 and 2010 at the Michigan State University, which is called Pride. In fact, many of us already know that with Scott, Sören demonstrated several important background contributions to CME observables, which we now know they are very important to understanding in the search for the Chiral magnetic effect. After that, Sören was doing his PhD in Heidelberg and got the degree in 2013. Then he moved to the Brookhaven National Lab as a Golden Hubble Finals. In fact, his office is opposite to mine. So then he moved to the INT as a research associate professor between 2016 and 2018. After that, he got a faculty position at the Bielefeld University, where he's loved. So we know that Sören, in my mind, Sören is solving the highly nonlinear dynamics with the sophisticated numerical techniques, including the QCD under the extreme conditions. And 2 days ago, he got the prestigious Zemanya Award for the young scientist, and based on his contribution in characterizing the initial stages of the heavy collisions and also the turbulent physics in the QCD in the far from equilibrium limit. So today, Sören will tell us about the another hard problem, which I think is also very important for the QCD critical research. He will tell us the dynamical critical behavior in the D2 and O4 universality classes. So without further ado, so now it's yours, Sören.
Yeah, thank you very much, Yi, for this great introduction, and thanks for the kind invitation. So indeed, today I'll be talking about dynamic critical behavior and 2 universality classes that are relevant to QCD dynamics. And so I really appreciate the opportunity to talk here, because this is work that usually I don't get to cover a lot. Started a long time ago with my bachelor thesis here, actually, but in recent years we've sort of become more and more active in this, and of course we're engaging further in this in the context of trying to understand critical behavior in the QCD context. So the outline of this talk is as follows. So I have a lot of material actually, and I'm probably not going to be able to cover everything. So at some point, you guys will have to tell me when to stop. Okay. So I'll start with an introduction and a motivation. So why is it interesting to look at the critical behavior, in particular in the models that we're considering? And then they will sort of transmute in a little bit of a more of a theoretical investigation of, what do we actually see when we study dynamics in the vicinity of a critical point. I'll go to models with dissipative and conservative dynamics. I'll then talk about relativistic diffusion. And then towards the final part, I would like to take this one step further, going away from equilibrium and actually studying sort of dynamical phase transition. So what happens when we send the system through a critical point on a dynamic trajectory. And I'll probably won't have time to actually talk about O4, but let's see. Okay. So let me start with the motivation, and clearly the motivation comes from the phase transitions that we see or that we expect to see in the phase diagram of QCD. So here's a little sketch that I like very much of the QCD phase diagram, which is actually sort of looks a little bit different than the ones you may be used to see. So this is a sketch of the QCD phase diagram that shows, in addition to the temperature and chemical potential axis, also the axis of light quark of the light quark mass. And so the usual phase diagram resides here in this back plane, right, where at zero density and finite temperature, we actually have a crossover, okay? But then what we expect is that as we go to lower, slightly lower temperatures and probably much higher densities, or relatively high chemical potentials, we expect to see this QCD critical point, and that one is expected to be in the Ising, so the Z2 universality. Now, in addition to that, there have been, my Lattice friends in Bielefeld have been very active, and also other groups, in sort of trying to understand what happens to the QCD transition as you change the light quark masses, okay? And so what happens then is that if you really can send the light quark masses to zero, is you're expected to encounter another critical point, which is related to the chiral phase transition of QCD, okay? And so this one is believed to be an O4 critical point, tying to the essentially O4 symmetry that emerges from the symmetries of the quark sector, okay? And well, actually that point is, the quark masses are not that heavy, right? So that point is actually not so far away, and it's sort of an ongoing topic also in terms of, how much that O4 critical point may actually affect the crossover transition that we see in real world QCD. Okay, so I've highlighted sort of these two landmark points, the O4 critical point and the Z2 critical point, right? And so of course that's something that this one we're not going to find because we don't live in the world of zero quark masses, but maybe we'll see, maybe we can actually see some remnants of it in the real world. Okay, but so how do we go about sort of finding out what's really happening at this critical points? And so of course there are major experimental efforts ranging in that direction, be it at RHIC or be it at Future Facility, that are really dedicated towards probing here this high density region. Okay, and unraveling the phase structure of QCD in that way, right? But so as we in this audience all know, right, is that, okay, when we're studying heavy ion collisions, right, these are very complicated systems with a rich space-time dynamics. So it's really not as simple as just looking at the phase diagram. That's really not what we're doing, right? But what we're doing is sort of a highly dynamical process in which we probe this, okay? And so as a sort of a first theorist kind of question that should probably come to your mind then is to ask not only, well, okay, there is potentially a critical point here, right? This we know describes sort of static properties, but we should also understand what are really the real-time or dynamical properties in the vicinity of such a critical point. So that's sort of question number one, and I'll try to say a little bit about this, although be it in somewhat simpler models, okay? And then the second question that you may ask, sort of going towards the complexity of a heavy ion collision, is that we don't prepare a system in a state that's just at a fixed temperature and chemical potential, but we will actually going to transit a point like this. And so we may ask the question, okay, how does one theoretically describe the passage of a system close to such a critical point? Okay. Okay, and I'll say a few words about this and sort of what are the phenomena that emerge. Okay, now of course what we'd ultimately like to understand is, okay, how do we really see this in experiments? And so there's much more, but I mean, to really be able to say something about this, I think it's much more complicated, right? One really has to make sure, I mean, what really sets these points apart is that in the vicinity of a critical point, the system exhibits universal behavior on long time and distance scales. But okay, for that to show up, we would have to make sure that actually the volumes of lifetimes that we can achieve in the heavy ion collision are sufficient to actually realize this universal critical behavior. And if so, it's still the question, you know, what are exactly the observables that we know. So unfortunately for my experimental colleagues, I'm not going to be able to address anything on the sort of the lower part of this. So, but instead, sort of the approach I would like to take is to say, okay, let's look at systems where we have we have good theoretical control, and let's really try to understand what happens. Okay, and since in the vicinity of a critical point, the physics is universal. Okay, if we can really realize critical dynamics in heavy ion collisions, then some of this may be relevant. Okay, so that's going to be sort of the line of attack underlying this whole study. Okay, so a few words about critical phenomena. I mean, I guess you've all heard this many times before in the seminar. Okay, but let me nevertheless sort of set the stage a little bit. So, of course, what makes these critical points special is that in the vicinity of the critical point, the correlation length of the systems diverges, and this has important consequences, meaning that the long distance properties of the physics actually become insensitive to the underlying microscopic dynamics, okay, or microscopic physics. And that's a very powerful statement because it allows you to study systems which are as complicated, or to study the universal aspects of systems which are as complicated as QCD in terms of very simple models of, say, the dynamics of a magnet, okay. And so the way that these static critical phenomena are characterized, so just for sort of equal time properties of the system, is that in the vicinity of the critical point, they can be fully characterized in terms of critical scaling exponents. So this is something that's well known, but then also scaling functions that really describe you sort of, you know, what is the functional dependence of deviations in the vicinity of the critical point, okay? And so all of these universal quantities, the static ones, really only depend on very few things, right? They depend typically on the dimensionality of the system and the symmetry breaking pattern that you have, right? And so I've said, okay, well, for QCD we're in 3 dimensions, and for the finite density critical point, we expect it to be in the Z2 or Ising universal. Okay, so this is static critical phenomena, and that's something that's, I guess, well known to all of us from, I guess, our graduate studies or so. Okay. Now, what's typically a little bit less known is when it comes to critical dynamics, what actually happens. Okay. And so, of course, when you're at a critical point, right? I mean, your system develops this kind of long-range order, right? And then you can imagine, like, now, if sort of domains of magnetization here for 2D Ising model need to change over time, right? And really sort of changing the structure of these large clusters can take a long time. And indeed, that's what you see. So what always comes in, what always comes together with the static critical behavior is the dynamic critical behavior, which describes a slowing down of the dynamics as characterized by, for instance, the divergence of a temporal correlation. Okay, and so similar to the static behavior, you can describe this in terms of an extra scaling exponent. So if you relate, for instance, the divergence of the autocorrelation time of the system to the spatial correlation length, then the corresponding exponent would be called Z. Okay, and in the vicinity of the critical point, this would diverge. Okay. Now, what is different from the static universality classes, or from the static behavior, is that, of course, now we're talking about dynamics of the systems, and there's a lot of things that can affect the dynamics of the system, even on very large time scales. Okay, and so one of them is, for instance, conservation laws, but also, for instance, the question: does your order parameter couple to other conserved quantities in the system? Okay, and so these are things that can affect. So this is what's typically called a mode coupling. Okay, so they affect the long-time dynamics. And so for a given class of systems which share the same static critical behavior, this can break up into multiple, so to say, dynamic universality classes, which are usually called models. Okay, and they've been classified in the 70s by Halperin and Hohenberg. Although this classification is not entirely complete, but usually one finds this. Okay. So where do we stand in so where do we believe QCD fits in there? So the QCD critical point at finite density is believed to be in the so-called model H dynamic universality class. And so basically what happens if you have a given static universality class, say 3D Ising, okay, then depending on what kinds of a dynamics you have, you would identify the corresponding dynamic universality class. So for model H, this means that the order parameter is conserved or has an admixture of a conserved quantity. In QCD, this would be the baryon density, okay? And it's also coupled to a fluid, okay, which would just be sort of the rest of the bulk energy momentum density, okay? So while I would very much like to tell you something about model H, I have to say right away, we are not there yet, okay? But instead, I'll be covering sort of dynamics I'll be covering what's the physics when the dynamics is slightly simpler. So the simplest case is that of model A, where you have no conservation laws and just sort of purely dissipative dynamics, okay? And I'll also be saying something about the case that happens when you have a conserved order parameter, so diffusive dynamics of, say, the baryon density, but no extra coupling to a fluid, for instance, okay? For completeness, if you look at the chiral transition, then this one is believed to be in the so-called model G universality class. This is because essentially the 4-component chiral condensate order parameter then also couples to vector and axial currents, which are conserved quantities. So that's a symmetry of these multi-component systems. Okay, so with that, I think I more or less set the stage. Okay, so let's dive in and let's sort of start to get a feeling by looking at the critical dynamics. And what we'll usually be looking at to characterize this are spectral functions of the order parameter. Okay, and we will start out very simple. So we'll look at this in just a relativistic scalar field theory, which is in this Ising universality class. And it turns out one really gains a lot of insight by sort of also comparing this in different dimensions. Okay, so I'll always be showing kind of results from 2 and 3 dimensions. Okay, now I should say a little bit about the methodology of how we do this. And so really here the goal is to take a completely unbiased perspective. Okay, so we want to do first principle simulations, okay, not do any kind of approximation. So the goal is to kind of probe this by direct simulation and just really see what the system wants to do and what it does. Okay. And this is generally, of course, hard because you have to deal with real-time dynamics. And in the quantum field theory, there's no sort of first principle approach to do this, okay? However, what's nice about these finite temperature phase transitions is that you don't have to study actually the quantum theory, but you can study a classical theory, okay? So the critical dynamics of a second order phase transition is actually classical statistical in nature. And the reason for that is that the quantum and the classical theory are in the same both static and dynamic universality classes, at least in the absence of anomaly. Okay, and classical theories is something that we understand very well. You can just directly simulate them in terms of real-time lattice simulations. Okay, and that's exactly what we're gonna do. Okay, so to study then, to study then critical behavior. Okay, what we're going to do in the simplest case is we're going to look at single component scalar field theory. So this is the Hamiltonian usual kinetic and gradient part. We're going to use a negative mass and a quartic self interaction. And this theory has a finite temperature phase transition whenever you put this mass square term negative, okay, and the order parameter is just the expectation value of the scalar field inside your volume, okay, and the universality class is in this case, so the static one is exactly the same as for QCD, so it's the Ising universality class. And the nice thing about this is in 2D we know, of course, exactly all the static critical behavior from analytic solutions of Onsager, and in 3D this is also known to very high precision, say for instance from conformal bootstrap. Okay, so how do we then proceed to sort of look at the critical dynamics? So what we do is a standard calculation in classical statistical field theory. So what we do is we generate an ensemble of thermal field configurations using standard importance sampling. Then starting from that, we solve the classical equations of motion. So for model C, this would be simply the Hamiltonian equations of motion. So model C is a non-conserved order parameter coupled with the conserved energy density. In this case, if you solve Hamiltonian dynamics, energy density is conserved. So you have a conserved quantity in the game. There's also model A, where in addition, you would allow for energy exchange with a heat bath. Okay, so there we would introduce a finite Langevin damping here to a heat bath, and then a stochastic noise. Okay, and so from that, what we do is we compute the so-called spectral function of the order parameter. So in the quantum theory, this would be simply the expectation value of the commutator of the order parameter field. In the classical theory, this maps onto the Poisson bracket, and there's an easy way to compute this just from unequal time autocorrelation functions by using the so-called, I wrote this here as KMS, but this is really the fluctuation dissipation theorem in the system. Okay. Okay. Questions up to now? Okay, I don't see any. So let's let's look at this, and let's so before we look at the result, let's sort of try to build some expectation. So if we look at the scalar field theory, right, then it's actually an interesting question to ask what happens, right? Because if we look away, if we look anywhere away from the critical temperature, then we all expect, okay, these are the effective degrees of freedom of this theory are somehow massive quasi-particles with potentially some finite lifetime. And if you calculate the spectral function, for instance, in mean field approximation, you would basically have some delta peaks, but then if you were to include perturbative corrections, these peaks would slightly shift in position and perhaps broaden. Okay. Now, if you contrast this with the critical behavior, okay, then in the vicinity of the critical point, the spectral function, which will depend on the frequency, the momentum, and the reduced temperature of the system, is expected to exhibit a scale invariant behavior, just like you know it for static critical behavior as well. Okay, the same holds for dynamic scaling functions with a scaling dimension that's or with a scaling dimension that's dictated by the scaling dimension of the order parameter. Okay, and then different rescalings of the time, momentum, and temperature axis. Okay, and so in principle we know what these exponents are according to the classification. So this exponent z is going to be somewhere around 2 typically in these models. Again, I've given the concrete values there. And so it's an interesting question to ask. What is the dynamics, or what is the changes in the spectral function that drive you from this sort of mean field like behavior to actually realize this critical? Okay, and this is essentially what we started to look at in the very beginning. So I'm often going to show you sort of plots which show the spectral function as a function of the frequency. Okay, and so here in this case, this is shown at 0 spatial momentum. So this is really just the spectral function of the homogeneous order parameter field as we extracted it from these real-time lattice. And so here you already see a very interesting behavior, namely if you look far away from TC, which would be sort of this orange curve over here, you see indeed, you have some well-defined quasi-particle peak. I mean, it's sort of has a broad width, right? But overall, it's actually very well captured by a bright Wigner field. Now, if you lower the temperature, okay, something very interesting happens. So first of all, your quasi-particle gets lighter, right? So you expect it to eventually, essentially become massless, or at least exhibit a minimum in the vicinity of the critical point. But then once you start moving closer and closer to TC, then what you see is that actually, in addition to kind of this quasi-particle, there's sort of a second peak structure emerging in the spectral function. Okay, and the second peak actually corresponds no longer to sort of a propagating mode, but this is really something that's more characteristic of just the relaxational dynamics of the order parameter. And this you see very nicely if you actually look at the spectral function also in the time domain, right? So usually if you have if you just have a sort of a quasi-particle peak, the way the spectral function would look like would be sort of have this damped oscillatory behavior. The frequency of the oscillation is the particle mass. The damping rate is the lifetime, okay? But then as you approach TC, essentially all this damping goes more or less away, and you're sort of dominated by just having a relaxation, okay? So there's really sort of the intuition kind of changes for what this degree of freedom looks like, right? So it goes from sort of being a propagating quasi-particle, at least at low momentum, to being really this sort of purely relaxational mode, okay? And in fact, if you go closer and closer to TC, which is now shown here on the right, so again, spectral function in the time domain, so this is really the critical region, then what you can see is that, well, that sort of the time scales for this exponential decay become longer and longer. And actually, if you go really close to TC, okay, then you'll find that actually the correlation function exhibits a power law decay in time, and in principle this autocorrelation time that eventually marks this exponential decay really diverges, and so from this you can in principle extract the dynamic critical exponents. Okay, so this was the behavior.
Excuse me, Sören. I guess
yeah.
I'm sorry, Sören. I guess Thomas has a short question. He's asking in the IR region, should IR be the equilibrium at any t, not just near TC? His question is.
What is he asking? Sorry, I didn't capture.
Maybe Thomas, can you simply quickly speak it out?
Yeah, I was wondering whether the infrared, whether that shouldn't be fluid dynamics, meaning kind of a Rayleigh and a Bielefeld peak at any temperature, not just TC. I mean, we always think that the long distance is fluid, isn't it?
In principle, it should behave as a fluid, right? But I mean, we're looking at the spectral function of the order parameter, right? We're not looking at energy density correlators or anything like that, right? And I mean, this is Hamiltonian dynamics, so energy is conserved. Momentum conservation, unfortunately, is broken by the lattice discretization, okay? So this may have an effect, but
I guess maybe we can continue afterwards. Yeah, so Sören, please go ahead.
Okay, yeah. Okay, good. So we see this transition. So we see this transition from sort of relativistic quasi-particles to really just relaxational dynamics in the vicinity of the critical point. And so all of this was really for the order parameter, so looking at zero spatial momentum, right? And so what we did in recent years is then to actually sort of go beyond that and now look at the full spectral function as a function of both also at finite spatial moment. And so this is sort of sketched over here. Okay, so now on the left, the behavior is shown in the symmetry broken phase. Here's the behavior in the vicinity of the critical point, and here's the behavior in the symmetry restored phase. And so essentially what you see here, what's a little bit highlighted in black, is essentially the way that this looked before. If we just look at the zero momentum mode, so in the high temperature phase, what you see is actually, you see that you have this well-defined quasi-particle peak, even at very low spatial momentum. But then if you go to the critical point, right, then sort of this high frequency tail seems to develop this very strong infrared enhancement for really the infrared modes, okay? Whereas, for instance, if you look at higher momenta, what you actually find is that sort of the quasi-particle structure of the theory actually remains intact. Okay, so it's really only these low momentum modes that eventually show the critical enhancement, and that's of course what you expect. Okay. What's also very interesting is that actually, if you go below TC, then sort of in addition to this again quasi-particle that we have away from the critical point, there's actually some kind of second mode emerging here, so some kind of soft collective excitation that vanishes at zero momentum. Okay, so that's why we didn't capture it before, but that's present at in finite moment. Yeah. And so this is sort of the situation for in 2D, but I mean here I have the same thing in 3D. It's just harder to simulate, but basically structurally the behavior is exactly the same. Okay. Okay. So I mentioned sort of the persistence of having this quasi-particle at higher momenta. Okay, so let's see what is actually dispersion of this, or what does this look like. So what we did is we kind of did some we did RHIC fit, so just fitted the spectral function with a sort of a finite mass and a finite decay width in the usual relativistic parametrization. Okay, and so this is shown here for different momentum modes in both 2 dimensions and 3 dimensions. So the full symbols are the particle mass, okay, and the open symbols are the decay width. Okay, we always subtract the momentum squared, so that's sort of like the effective mass of that mode. And so generally what you can see is that as you approach the critical point, essentially the effective mass experiences a minimum, then it starts to rise again in the high temperature phase, even better visible in 3 dimensions. Okay. And the decay width sort of gets a little peak, maybe best seen here, for instance, in the blue one. But overall, actually, what's very nice to see is that I mean, the behavior of these higher momentum modes is really continuous across the transition, and you just have minima and maxima in the dispersion relation and the decay rate of this. Now, of course, this is different. This is completely different to what happens to the infrared modes, okay? Because the infrared modes really show this strong enhancement. So the infrared, so the low momentum modes, right? And they actually do realize this critical scaling that I showed earlier. Okay, and so the way they do this is actually is actually in a very interesting. So if you have a scaling law like this, okay, what you can always do is you can kind of choose your scale factor such that you, for instance, try to map the behavior for different momenta onto each other. Okay, and that's essentially what we tried to do in this plot here. So we calculate the spectral function at different frequencies for different momentum modes. Okay, and then we try to scale them on top of each other to essentially single out what is the underlying scaling function that emerges here. And so if you do this at the critical point, then this argument is just 0. Okay, and you can parameterize essentially the spectral function in terms of, I guess, this one scaling function over here. Okay. In principle, there's one scaling function that begins on 3 arguments, but if you set one of them to 0, you essentially get you get a 2-dimensional scaling function. Okay, and so really, when you do this, what you see is that indeed you check this out for different momentum modes. So relatively high momentum, a little bit smaller, yet smaller in the red. Okay, indeed you find this very, very nice scaling collapse. Okay, and essentially what this scaling function does is it interpolates between different types of behavior. So on the one hand, if you look at very, very low frequencies, so which is very, very long times, okay, and you don't have exactly the critical mode, so exactly 0 momentum at exactly the critical point, then on these large time scales, you're basically again going to see regular dynamics, okay, and so in this case, actually what we find is that the scaling function is just sort of given by a simple proportionality to this scaling variable, I mean, essentially linear in the frequency, okay. Now, if you look on the right of this thing, which corresponds to time scales which are shorter than the autocorrelation time of the system, okay, then what you actually see is you see the critical dynamics of the system, okay, and so in this regime, the spectral function actually exhibits a power law dependence on the momentum. So it goes as omega to the -2 minus eta over z, okay, and so that's basically captured by this black line here, okay, and so that's what this spectral function collapses onto, okay. So and of course, for every finite momentum mode, right, eventually at some point you're going to resolve the microscopic structure of the theory. So like at any momentum, there's kind of a point where it breaks down, and that's actually sort of where these quasi-particle or where remnants of the quasi-particles typically still live. So you see at higher momenta, sort of the scaling breaks a little bit earlier in the scaling variable, but then if you really go to low momentum, then in principle you cover the full scaling function. So the bottom line is that actually, if you really care about what is the universal dynamical behavior of such a theory in the vicinity of the critical point, it can be captured by knowing the static and dynamical critical exponents and by knowing the form of this one such scaling function, which in this case we calculated for these scalar field theories, and it's basically given by this black form. Okay. Yeah, so this is just sort of to show you that this is not a singular case. So you can do this. You can do this with dissipative dynamics in the top. So this is 2 dimensions, 3 dimensions. You can couple this to energy conservation, or in our case, just realize Hamiltonian dynamics. So in that case, you have. You also have energy conservation, of course, and the scaling functions themselves, they look different, right? Because you're looking at different theories. So the scaling functions at the end are different, okay? But within every given model, you find the collapse of all these modes to this dynamic scaling function. And this is really very nice, right? This is a really explicit verification of this dynamical scaling hypothesis and explicit determination of what the dynamics looks like in the vicinity of the critical. Okay, are there questions? I could take some here. Otherwise, I'll move on to
I think so hi Sören, I think a quick question which may also be asked by earlier is why we do not see any hydrodynamic pole contribution in all those spectral functions.
I mean, so maybe we can postpone this discussion for later, okay? Because I'm not sure what the people who are asking these questions are actually exactly referring to, or what exactly they want to see, so to say. Yeah. Okay.
Okay, we can defer.
Yeah. Maybe this will emerge better after the diffusion part. Also.
Sören,
yeah.
May I ask a question? So there was 3 variables in your function: omega, p, and tau.
Mm-hmm.
So where is tau in that plot?
So this is at the critical point. That's what I was trying to say. So I set the I set the critical. So this work is working at the critical point and looking at the scaling as a function of frequency and momentum.
So tau is equal to 0.
Yeah. Yeah.
Okay. Mm-hmm.
Yeah.
Thanks.
Yeah. The problem is, the problem is, it would be nice to sort of map out this function in more dimensions, but it's a hard job, right? I mean. But
yeah, I just lost this. I think I see it now on your plot. There's f of xp comma 0. So that 0 is tau, right?
Yeah. Yeah. Exactly.
Mm-hmm.
Exactly.
Okay.
Yeah.
Thanks.
I think there's another question from the chat by Dr. Basai. So his question is: do you see this scaling in a fixed volume? Is no finite size scaling necessary to get the scaling behavior?
No, this is a good point. So one of the things that we sort of learned the hard way is that, I mean, of course, if you look at the 0 mode of the order parameter, right, at some point, if you go close enough to TC, you're always going to be bound by finite size effects, and then you will see finite size scaling, okay? But what turns out to be the case is that actually for these finite momentum modes, okay, you can really, I mean, you introduce another infrared cutoff, which is the momentum essentially, okay, and then you can actually take the infinite volume limit, even at TC. I hope that answers the question. Okay. Okay, good. So then let me come to the second part. How much time do I have in total? I have an hour or 45 minutes?
I think approximately 1 hour.
Okay, good. Okay, good. So then I will.
So you have 23 minutes.
Yeah. Okay. So then I will actually talk about diffusion. Okay. So so far we considered sort of the simplest possible model, right? Where the order parameter was, was simply a scalar field with dissipative dynamics, or with Hamiltonian dynamics. Okay, but now, of course, you can also encounter the situation where the order parameter corresponds to conserved density, for instance, the baryon density, or in fact, even if it just mix it with it, then the conserved density will sort of always win. Okay, and then you need to consider modified equation of motion. Okay. And so in the way that this is usually realized in this non-relativistic literature is just that, say, just look at the top equation here for your order parameter. You would consider some kind of diffusion equation, okay, where essentially, the change of the time of the order parameter would be given by, if you want to, the divergence of a diffusion current, okay, and there would be noise, which also is such that it conserves the overall order parameter, okay? And in principle, you can then take your order parameter and couple it to other fields if you want, such as a conserved energy density, that would be model D, but in general, if you just have the first equation, okay, just a conserved order parameter without anything else, this is what sort of is the next level of quantification that's then called the model B, okay? Now, of course, one could just look at that, okay, but somehow I guess in our community we're sort of more interested in what happens when we do this with relativistic diffusion, okay. And so what we did is we considered a sort of standard Israel-Stewart type diffusion equation, okay, where instead of being instantaneously determined, the diffusion currents relax to their Navier-Stokes value on a time scale of 1/gamma. Okay, so the equation of motion is then essentially just current conservation. The current is the order parameter times the fluid velocity, and then there's a dissipative part. We don't actually couple to a fluid, so this is just the system is just at rest. Okay, but then this dissipative current only relaxes to its Navier-Stokes value, which is given by gradient of the of the HD phi, so of the derivative of the Hamiltonian with respect to the field. Okay, and there's also stochastic noise. Okay, which essentially accounts for stochastic diffusion. Okay, and so of course this doesn't change anything about the static critical behavior. Okay, so static behavior is untouched. Okay, and I mean your equilibrium probability distribution is still stationary under this, but this will of course modify the dynamics of the system. So for instance, it would make absolutely no sense anymore, okay, to look at the zero momentum node, the dynamics of the zero momentum mode, because that just corresponds to the net charge in your system, which is now a constant. Okay, so there's nothing interesting that's gonna come in. Okay, so what is interesting about this, or about this Israel-Stewart type formulation of this, is that if you look at actually the kind of excitations that this hydrodynamic equation, or this conservation equation features, even just at the mean field level, okay, then if you're at low momentum compared to, if you're at low momentum compared to essentially your mobility constant and your relaxation time, okay, then what you will find is that if you calculate your retarded propagator, essentially there's one diffusive pole, which basically has the same behavior as non-relativistic hydrodynamics, okay, and then in addition to that, there's a non-hydrodynamic mode, okay, that characterizes the decay of your currents to their Navier-Stokes values. Okay. However, if you go to high momentum, actually something interesting happens. Okay, so the model essentially, so these two modes merge. Okay, and then they kind of repel each other, and they become sort of two propagating modes. Okay. And actually, you have, in this case, you have a conserved order parameter, okay, even without having actual diffusive dynamics, okay. So that's something that in the non-relativistic case never happens. And in particular, if you take the limit where this gamma goes to 0, so this would be the limit in relaxation time to infinity, okay, then at least at the mean field level, that's actually the only thing that kind of survives, okay. Okay, so let's see what happens when we do this in our simulations. And so here again are sort of pictures of the spectral function as you go across the phase diagram. So left is 2 dimensions, right is 3 dimensions, I guess. I cannot see what's on the slide. And so if you start at high temperature, so this is usually again the simplest to understand, what you find is that at low momentum, I mean, you can analyze the dispersion and so forth. Indeed, you see these kind of structures. So these correspond to standard diffusion peaks. But then if you go to sort of higher and higher momenta, you actually see that you're dominated by this non-hydro mode. So you're in this other regime where you sort of have, again, propagating excitations, but in a way that they still conserve the charge. Okay. In this case, what's actually interesting is that near the critical point, okay, you see, well, there is an infrared enhancement, but as we'll see very shortly, okay, actually the spectral functions themselves stay very, very close to their mean field form, and it's really just the frequency and momentum dependence of these of essentially the damping rate and the and sort of the diffusion constant that actually make up for the critical behavior. Yeah. And so in the low temperature phase, also nothing sort of spectacular happens. Okay, so in the symmetry broken phase, again, it looks like normal diffusion, and in the ultraviolet, you have these non-hydro. Okay, so let's start to look at this. So let's look a little bit more at the critical spectral function. So this is again now tuning to the critical point in 2 dimensions, and we do this at a finite relaxation time here. Okay, so this shows again the spectral function as a function of frequency, double logarithmic plot. Okay, for different momentum modes, so going from high momentum to lower and lower momentum, blue, green, red. Okay, and so one of the things that's really somewhat surprising is if you look at these black curves, then what these black curves represent is just fits to the mean field form of the spectral function, okay, but now allowing for a momentum dependent essentially for a momentum dependent diffusion constant, okay, and for a momentum dependent decay rate, okay. So this omega p squared, this would be, well, if you divide it by p squared, this would basically be the diffusion constant, okay, and in gamma p would be the inverse of the relaxation time, okay. And so away from TC, they're sort of given by this mean field type form. And what happens is that actually you can still describe the critical spectral functions, particularly in 3D, very, very well by this form, okay. But what you have to account for is that now both the diffusion constant as well as the relaxation time, if you want so, they experience critical scaling, so they experience a power law behavior on the moment. Okay, and so this is actually what will then give rise to the critical dynamics. So you can tune this, so you can of course look at what these fit parameters do, and so this is now shown for different damping rates. So red is actually the case where we take the relaxation time to infinity, and then we have two cases with a finite relaxation time. Okay, let's maybe look at the 3D case, which is easier. So let's first look at the behavior of the diffusion constant. So you have a very nice power law. You actually also have a power law here. It just gets harder and harder to fit. So this power law essentially has a characteristic momentum dependence, which is actually given by 4 minus the static critical exponent eta. Okay, and yeah, I think this is what the black line that's essentially on top of this behavior really shows. But now what's sort of interesting is that since you have this kind of mean field form, okay, you can look at what this relaxation time does, or the inverse of this relaxation time does. Yeah? And so whenever you have essentially a finite relaxation time to start with, okay, then basically this induces, so if you want to, some dissipation in the system, and in the infrared, essentially the behavior will always go to this finite constant, or to this finite Baire damping that you put in, okay, and so this simply becomes constant, and if this becomes constant, then actually the entire dynamic critical exponent is just given by this 4 minus eta. Yeah. What happens when you take out the dissipation, in which case you again have a conserved energy, so one would expect this to classify as model D usually, okay? But in this case, what happens is that actually the damping rate also exhibits a power law behavior, okay? With actually, again, sizable exponent sort of in the range 1.5 or something like this, okay? And this will actually then change the critical exponent. So for this relativistic model D, we actually don't find the same dynamic critical exponent as the end as for this model B, which is different from sort of the non-relativistic literature. Okay, yeah, and so this is actually that's actually what you can see here. So you can now calculate the autocorrelation times, and so typically what you will find is that, well, they diverge as a function of the momentum at the critical point, okay, and the divergence again gives you this exponent 4 minus eta, okay. But then if you do this for short relaxation times, you see this very nicely, and as you sort of make it larger and larger, then you actually start to first see this dynamics of the model D-like system, so of the system which has infinite relaxation time, and subsequently, you know, at very low momenta, of course, if it's finite, you start to depart and you start to see the true critical behavior of this model D. Okay, now let's look at the spectral function. So you can again do the spectral function. In this case, this is really super nice. Okay, because I mean, I told you the spectral functions are actually very well described by their mean field form. Okay, you just have to account for the momentum dependence of the diffusion rate and the damping rate. Okay, and indeed, also here very nicely. Okay, if you look at now again critical spectral functions. Okay, and you compare different momenta, you can again find this very nice scaling collapse, that the whole spectral function is again described by one universal scaling function, which in this case I can give you an explicit analytic form, which is basically just determined from the mean field behavior and the power law dependence of the kinetic coefficients, if you want, so of the diffusion constant and the damping rate, okay? And so these black lines in this case are actually not even a fit, okay? They're actually really just determined from knowing the amplitudes and knowing the mean field form. And as you can see in all of the cases that we have, they really describe the data that exhibits the scaling collapse very well. Unfortunately, in these cases where we really sent the dissipation rate to 0, okay, we are not able to really go to low enough momenta or large enough lattices to have low enough momenta. But I think it's very indicative that sort of these curves will collapse onto these black curves. At least you see it very nicely in 2 dimensions, and in principle, there's no reason to doubt that the same thing will happen also in 3 dimensions. Okay, so I think I still have 10 minutes, so let me come to the last part that I really want to cover here today, which is, so far I've always been talking about dynamics of an equilibrium system, okay? And now I would like to go one step further and actually ask the question, okay, how can we now use this information, or how can we now understand what happens when a system actually dynamically goes to a critical point, okay? And of course, that's also what's going to happen at the end of the day in a heavy ion collision, right? Because we cannot take our system, have it sit there forever. No, in the best case, we're going to have a reasonably large system, okay, which reasonably slowly passes by the critical point, okay? And so what we're going to do to explore that is we're going to look at the same model again, scalar field theory. In this case, this was first done in 2 dimensions, okay? And we're going to start somewhere at the critical temperature with a finite explicit symmetry breaking. And then we're sort of slowly going to change that, go through 0, pass the critical point, and come out on the other side, okay? Now, something like this is called a transcritical protocol, okay? And so let's first build an expectation for what should happen. I guess some of you know this very well, okay? But so the point is that as you approach the critical point, right, we've seen that, okay, the autocorrelation time or the relaxation rates in the system diverge, right? And so as you get closer and closer to the critical point, at some point, the system will have no longer time to kind of stay in equilibrium, okay? And so it will fall out of equilibrium, okay? And this will happen at some kind of finite time close to the critical point, okay? That's called the Kibble-Zurich time, okay? At this point, the system has some particular temperature, in our case, the critical temperature, and some particular magnetization, which is called JKZ, okay? And so it falls out of equilibrium when essentially the change of the order parameter relative to the order parameter, okay, becomes faster than the way that the system can relax, okay? And what is predicted to happen in this case is the so-called Kibble-Zurich scaling, okay, where the non-equilibrium dynamics near the critical point is again governed by a universal scaling exponents, okay, but now these are related to the points in time and the properties of the system in time where the system actually founds out of equilibrium. So it's related to the scaling that you usually have in terms of the temperature and the magnetization, but now at the point in time where approaching the critical point, the system falls off. Okay, so to look at this, my very talented bachelor student Mattis actually did a plethora of simulations, okay, where essentially what he did is he tuned the system to the critical point and considered a linear variation of this explicit symmetry breaking, and then monitored the evolution of the order parameter, but also the higher order cumulants of the system, okay. So in the bottom, you can see how for sort of different quench times, so it's called a quench in condensed matter literature, okay? For different quench times, we change, so we start at this point here, then we change the explicit symmetry breaking in sort of a linear fashion, okay, until at some point we arrived at the end, okay, and then we leave it there, okay? And so, okay, so what you can see is if you now look at, for instance, the evolution of the magnetization, right, then you can see, okay, here, so for some cases, okay, essentially the magnetization first starts to grow, but then here at this time, for instance, where you would have the zero crossing, actually the magnetization is still negative, okay, so it still lags behind, okay, and so clearly by that time the system has already fallen out of equilibrium, right? And so so you see this very nicely, that sort of the faster you make the quench, okay, the system will, well, going in this way, the slower to make the quench, the system will fall out of equilibrium, okay. But what's sort of interesting to see also is actually if you look at the order parameter and then the susceptibility, the skewness, the kurtosis, okay, is that actually sort of the characteristic features that you usually see when you encounter the phase transition. So here the zero crossing, here the peak, here again 2 peaks and a zero crossing, and here this sort of double hump structure, okay, they still remain the same. And actually these higher order cumulants very much follow the behavior of the order parameters. Kind of these characteristic features really appear on the same time. Yeah? And so the prediction now for this, from this Schlichting scaling is essentially that, well, on the one hand, the point in time where these things happen has a particular scaling with the quench rate, so with like the speed at which you pass the transition. And on the other hand, also the amplitude, as you can see, the slower you make your quench, the larger the enhancement gets, okay? And that also, well, you can kind of see it here, that also has a very particular dependence on the quench time. And so indeed, you can look at sort of how this depends on the quench time. So if you look at this criterion, that sort of the change of the order parameter becomes fast compared to the autocorrelation, inverse autocorrelation time of the system, okay, you can determine how this Kibble-Zurich time scale should behave as a function of the quench time, okay, so this is given through a combination of static and dynamic critical exponents, okay, in this case, this turns out to be roughly a half, okay. And indeed, if you look, so, you know, my student extracted all these features, okay, and you see, okay, very nicely, I mean, this purple line is essentially the prediction. This is a plot of sort of all the different features, so zero crossings of the order parameter, position of these minima, maxima, and so forth, that indeed you have a very nice scaling with precisely the exponent that you would expect, okay. So that's very nice. So that's really sort of an explicit confirmation that we see this Kibble-Zurich scaling, okay, and that we see it not only in the order parameter, but we also see it somehow in the higher order cumulants, okay. And then the next thing you can ask is, well, okay, so now you have the scaling of the time at which it happens, right? How about the scaling of the amplitude? Okay, and so again, actually, the theory makes a prediction for how this should go. So for this particular quench protocol, the amplitude or the height, how strong is the say the enhancement of fluctuations in the system, should scale with the magnetization at the point when you fall out of equilibrium. Okay, so this is the statement in the infinite volume limit. If we use exactly this exponents, we actually don't see a very good collapse. Okay, so we find roughly this, but not exactly. Okay, so you see we can get this to collapse more or less, at least in the vicinity of the critical point, and then we essentially have this kind of standard features like how the order parameter looks across the transition, how the fluctuations move across the transition, skewness, kurtosis. Okay. However, yeah, we don't yet fully match the exponents, but we also have some indications that actually, so these simulations are already done on, I mean, they're very expensive, they're done on pretty large lattices, but I think we still have to go to larger lattices and really eliminate the finite size effects here in this case, because in this case, we're actually really looking at the fluctuations of the zero mode, and for the slow quenches, apparently, we're hitting the finite size scaling. Okay, so with that, let me skip everything that's related to 04 and let me actually just conclude, because I think I've used up my time. Opa. Okay, so summary and conclusion. So in this talk, I motivated that it's very interesting and important for us to, I think, really understand what's happening in the vicinity of a critical point, okay, where the dynamics is governed by universal scaling functions and scaling exponents, okay. And in our studies, we have started, to extract these things for a number of models. So models A and C, which are governed by relaxation dynamics, and models B and D, which are governed by diffusion dynamics. Of course, this is not QCD yet. So QCD would reside in the dynamic universality class of model H, and that's of course something that we have on our agenda to do. Now, these equilibrium studies, in a sense, they provide a baseline for studies of non-equilibrium phase transitions, and so that's another thing I showed you at the end. So from doing these simulations also in a setup where we transit the critical point dynamically, we actually see from these first principle simulations nice evidence of Kibble-Zurich scaling in these transcritical quenches. Okay, particularly we also see it very nicely, and I think this is. I mean, well, for the order parameters, it has certainly been done also in the condensed matter literature. I'm not sure about the higher order cumulants. So we also see this for the higher order cumulants. Okay, and so really what we hope to do is from this, again, I showed you there's kind of a scaling collapse. So again, there's universal scaling functions associated with this. So we hope to extract also these non-equilibrium scaling functions for the various 2 and 3D models. Okay. Yeah, and so with that, let me thank you, and I look forward to more discussion questions. Thanks.
Okay, yeah, sorry. Thank you so much for this nice presentation, and also I think you are doing very well in the timings. And so let me, if you have questions, you can raise your hand, but I will first go through the questions in the chat. I think there are several questions about the those here. I think we need to clarify. And the first question is asked by, I think, Kosi, if I pronounce it correctly. So, Kosi, are you still here, and can you speak out?
Oh, yes, yes.
Okay,
yes.
Thank you.
Yeah, thank you, Sören. It's a very nice talk. I learned a lot from you. So, a small question, maybe I can check by myself. So, after taking the conservation law into consideration, you said that in the vicinity of critical point, the spectra as Breit-Wigner form, right? So of course you have some parameters in this Breit-Wigner form formula. They of course they obey some scaling rule. So I just wonder, like as a whole, like the spectra as a whole, does it still obey the scaling rule you listed like several pages before?
Yeah, so let me make one comment here. So when I said Breit-Wigner form, of course, this is sort of the mean field form for this model. This is really what I mean by this. Okay, so in particular, the spectral function is very explicitly proportional to momentum squared. Okay, so it's right. So the zero channel. I mean, at zero momentum, you actually have nothing, right? Because you have a delta function, right? You just have a conserved order parameter, right? And this p squared is really the p squared that comes from diffusion, so to say. Yeah. Now really your question was, does sort of everything scale? And the answer is of course not, right? So somewhere, at some point you're going to see, in this case, the microscopic diffusive theory. Okay, and you can typically see this when you look, for instance, when you go here to high momentum or so, right? Then you see, for instance, okay, in this case, yeah, or even in this case, like your damping rate gets renormalized in a non-trivial way, so it does exhibit some momentum dependence, and so does the diffusion constant also. Yeah, I mean, subleading momentum dependence beyond that power law. Yeah, so there's always going to be a cutoff scale beyond which you're going to see essentially the microscopic dynamics. Yeah, so in this case, diffusion. Yeah.
Okay, I see. So can I say like this? So the conservation law to some extent breaks the critical scaling.
No. I mean, this has nothing to do with the conservation law, really, in that sense, right? I mean, that's just the critical dynamics is only for it only emerges in the long wavelength, low frequency limit, so to say. Yeah. And I mean, the surprising thing here, just to say that clearly, is that it can be so well captured by the mean field form. Yeah, that's something you usually wouldn't expect. So you expect to see scaling, right? And in the case of the non-conserved order parameter, we see these rather non-trivial scaling functions. Okay. But yeah, in the case of diffusion, it's just very simple. Okay, we can just find a very simple parametrization of the scaling function, which fits the results extremely well. Yeah.
Okay. Thanks.
And for Thomas, I think Thomas Schäfer also has a question or comment. So Thomas Schäfer, can you speak out?
Yeah, I think that was just part of the same discussion. I was actually slightly confused exactly how the conservation law arises, because at short distances, this is just real-time evolution of the Hamiltonian of a real scalar field theory. So in that theory, there's no conserved field. So this conservation law that somehow emerges at large distances.
No. So sorry, Thomas. So maybe you missed it. So I switched. So in the first part, I really just studied either Hamiltonian or Langevin dynamics, right? Then when I switched and I used Israel-Stewart equation essentially, right? So then then the conservation equation of the current is equation number 1, right? And just that the Navier-Stokes current is determined by the divergence of
But then you don't solve. Then you don't solve Hamiltonian dynamics anymore. You actually do fluid dynamics.
Yeah, I mean, we solve the equations that are written here.
So it's no longer Hamiltonian dynamics, is it?
Here it's no longer Hamiltonian dynamics. Exactly. Yeah. So here I'm doing diffusion dynamics, right? So yeah, very simple hydrodynamics if you want. So yeah.
And in the chat box, there's one more question from Horowitz. And Horowitz, can you speak out?
Yeah, thank you. So this is Will Horowitz, and I was just wondering if there were any analytic calculations you can compare your numerics to, especially say for the 2D, 3D scalar dynamics at the start.
Yeah, so of course, so when it comes to the critical exponents, absolutely yes, right? So I mean, they have been calculated from different approaches essentially. I mean, there are calculations in say dynamical renormalization group also. There are results there, and so generally we fare okay. We fare well in comparison to that, but it's very hard to determine them, of course, from this kind of lattice Monte Carlo studies. With regards to the scaling functions, actually not that I'm aware of. Quite honestly, yeah, and I mean, so we're trying this also with the real-time functional renormalization group, but we are, I mean, we're not there yet, I should say. Yeah.
But maybe just to very quickly follow up, you don't see any sort of fundamental reason why they cannot be calculated analytically.
I mean, calculating these scaling functions is usually much harder than studying than calculating the critical exponents, because the critical exponents, basically what you need is just you just need to know how the different couplings renormalize essentially in your theory, and then you can get this. Calculating the scaling functions is harder. Okay.
Thank you.
So maybe a quick question. I'm confused. Isn't it true? If I'm solving something like a Carnot symmetric type of equation, I should determine the scaling function.
I mean, usually if you solve Carnot symmetric, right, you just flow your couplings, no?
But also correct. Okay, yeah, maybe I should first go through the hands that are raised up. I think George Noronha was raised his hand first. So George, can you speak out?
Hi, thanks. So thanks, Sören, for this great talk. So precisely about this slide. So you have this diffusion dynamics and you create a relativistic model that had a relaxation time, right, for this conserved order parameter. But you could do the same thing in a non-relativistic system, right? So you had diffusion, but then you create a non-hydro mode in the non-relativistic theory, right? What would be the difference? So what does relativity bring as a new thing for this?
No, I don't really think I don't really think it fundamentally brings anything in this. I mean, in particular in the way, or at least not in the way we used it, right? I mean, as you can see here, right? I mean, in the first line of this, I just say, okay, my fluid is static at rest, right? And so in that sense, it's actually kind of what we're doing, right? We just write it in a relativistically covariant way, right? But I mean, what is interesting is that you get this non-hydro mode, and that in particular, if you go to the limit where this dissipation is zero, so to say, right, or where the relaxation time is infinite, right, that there you fundamentally alter the way that you achieve conserved dynamics. Yeah.
Okay, but you could repeat this calculation in a way that the U mu is not just 1, 0, 0, 0. Do you expect any fundamental difference qualitatively and quantitatively?
Well, I mean, well, okay. I mean, if you were to actually couple this to a fully fledged fluid, right?
No, not a fully fledged fluid. Just a standard thing moving at a constant velocity.
Ah, so you want to you just want to advect it?
Yes.
Basically. No, I mean, then you should see the same thing, right?
Okay. If the
I don't think it should change anything.
Okay, so you could have done all of this just in a standard non-relativistic notation, and the physics will still be the same.
I believe so, yeah.
Okay, thank you.
I think the next question is from Dr. Brasai, and if I pronounce it correctly, so can you speak out?
Yeah, so let me ask a question about the non-equilibrium part, which was very interesting, I find, where you are doing very similar thought experiment what Krishna Rajagopal did a couple of years ago, or a decade ago, actually. Exactly this. How does what you find depend on the university class, dynamical class? Because I guess you did the dissipative dynamics. If you have a Hamiltonian dynamics, of course, when you do a quenching, there is an overshooting of the operator, and then there's a dissipation afterwards. So the response is very much depending on what you assume otherwise from the system. So what are the assumptions what you have? And if you move on to this system A or model H, what would be different, or what are your expectations?
Yeah, this is I mean, this is a very good point, and it's also an excellent question. So just to clarify, so what we're doing here is this model A, dissipative dynamics, because that's the easiest, and then in principle you can also realize whatever trajectory you want, right? You could also change the temperature, right? Which, if you do it with Hamiltonian dynamics, you have to be a little bit more clever, right? You have to expand your system or something like this, right? Now, if you do model H, then there would be two things, right? There would be the order parameter would be conserved and essentially, I mean, I must say this, never sort of say too far in the future that I could really project an expectation. But I mean, so the goal of the study, and I'm glad you mentioned these earlier works. So there was this very old work by Rajagopal, and also Yi and collaborators looked into this. Probably also some time ago already now, right? And we just wanted to take, totally unbiased perspective, not have to do any approximations, that you just do an honest to God simulation and see what happens, right? Yeah. And essentially to have this as a benchmark for then, devising analytic treatments where you can add complexity that you want to have when you really model this inclusively.
Okay. No, very nice. Thank you.
Okay, the next question is Travis Doro. Are you there? Yeah, please ask.
Hey, yeah, thanks. Hey, Sören, thanks for the really nice talk. I was just wondering, actually, maybe something a little bit more simple. If you said it, I kind of missed it. But how, for this non-equilibrium phase transition part, how far from equilibrium could you be to still see this Kibble-Zurich scaling? So is there any way to quantify like how close to equilibrium you are, and we're able to?
So I guess what you, yeah. So I guess what the way this is set up, okay. But that's a very interesting question that you're raising. So the way that this is set up is that when we start our trajectory, we are in equilibrium. Okay, so we thermalize the system at a well-defined temperature and symmetry breaking, and then the system falls out of equilibrium, right? Only because it approaches the critical point.
Okay.
Yeah, no matter how slowly we quench it, close to critical point will always fall out of equilibrium. That's the beauty of this, essentially, right? Now, it's very interesting to ask, okay, would you still see something if for some reason, like in a heavy ion collision, the system was out of equilibrium to start with, right? Like say somewhere up here, and then you start changing, right? Sure. So, but yeah, I have no insights into this at the moment. Okay.
Yeah, I mean, in that sense, there'd be some competition between falling back into equilibrium because of the dynamics and driving it away.
So you would expect, I mean, of course, if you do it slow enough, you will be able to thermalize first, and then then see the Kibble-Zurich scaling. But if sort of things happen at the same time, then I mean,
yeah,
I'll probably break down, right? Unless some miracle occurs or something.
Yeah. Okay. Thanks a lot.
Okay. Next question, Misha.
Hi, Sören. Very nice talk. So just on this slide, as I understand, you are going through this critical region on the crossover side. What can you say about this transcritical protocol if you try to cross the first of the phase transition? Any insight?
Yeah, so this is a very good. No, so actually what we're doing, so I moved the arrow a little bit wrong, right? So the results I showed here on this slide is actually going exactly to the critical point, so to say. I mean, to the precision that we could determine it, right? And we have looked a little bit. Indeed, we have looked a little bit towards the other side, and basically, I mean, basically you still find these in the crossover side, and basically you still find critical enhancement there. We haven't really analyzed to what extent it still scales and things like this, right? But you find, let's say, qualitatively a similar behavior. Now, I haven't looked, now we actually haven't looked, well, maybe we've done simulations, but we certainly haven't understood really anything what happens if you do it in the, first order side, right? I mean, but there you would try to expect to see phenomena like hysteresis and so forth, right? So yeah, I mean, I would actually be very happy if somebody explains me what you should be seeing there, and we'll be happy to look for it. Yeah.
Thanks.
Okay.
Yeah. Thank you so much, Xiaofeng. I think last now I see the last question is from Lori Yuki Sakbe. Can you speak out?
Hi, Sören. Thank you for nice talk. I have a question on model B study of yours. Could you go back to that slide that you want, what you did explain? Or maybe the formulation. Next slide. This one. Thank you. So yeah, I have. So just look at this slide. I think you also I understood you did some hydrodynamic study with critical point governed by this model B type evolution equations. And yeah, compared to the conventional work, I think the presence of this kind of non-trivial pole structure is absent in the literature, like minus I gamma, minus I, and also the second one you mentioned, propagating mode. The existence of that did not include in say model B in Hohenberg-Harperin.
So the point is, so the point is, if you're in the usual model B, right, you have some finite relaxation time, then okay, you have your diffusion pole and you have some extra non-hydro mode. In this case, the extra non-hydro mode doesn't really do anything. Okay, in this case, we find basically the standard model B result, right? The interesting point is that this model, or this way of writing the theory, or this way of doing the conservation, allows you to also kind of realize this situation, right? So the situation of infinite relaxation time, right? Where then the structure is really different, right? You have charge conservation, but somehow to propagating mode. And there we find something that's, well, I mean, that's not the usual model D.
Yeah, I think so. But yeah, I'm wondering the nonlinear couplings on this gamma are affected or not due to the all the parameters. So did you look at that point?
I'm not sure I understand the question really.
So I mean, yeah, for maybe too naive, but I just expect this bare coefficient gamma can also affected by some renormalization effect.
Yeah, sure, and it is, right? So I mean, this is what I was, sorry, maybe I was not clear on this. So this is what I was trying to convey here, that if you set it to a finite value, then in the infrared, it's actually not renormalized, and you know, it has some additional small momentum dependent contribution, okay? But if you set it to 0, then you will build up something like this, right? And that exhibits a power law dependence. And that's at low momentum, what else should it do in the vicinity of the critical point, right? And that affects the critical scaling at the end.
I see. So you mean this gamma also shows some critical
So this capital gamma, if you want, so is the renormalized small gamma. I mean, that's at least one way to think about it. Yeah.
Okay, thank you. And another question, maybe out of scope of your work, but so if you want to realize some model B type critical dynamics from your analysis motivated analysis of the first part, what do you think you need to do?
Model B.
Yeah. So your
I
first.
mean, Model B we did, right? I mean, Model B we did, right? Model B you can just do. I mean, you can just.
Yeah. I knew. Yeah, but if so, but in your first part, you use some quantum classical simulation from the Hamiltonian, microscopic Hamiltonian, right?
Yeah.
And yeah, I knew this is different work. So yeah, this work from the hydrodynamic side is fine. But if one wants to study this kind of conserved or the parameter system from the Hamiltonian,
okay, I see.
Yeah, do you know what?
That's a good question. I haven't thought about this actually. I haven't thought about this. I don't have an answer out of the top of my head.
Thank you. So on the Model C, you mentioned about the Model C in the Hamiltonian.
Yeah, Model C is simple because Model C you just do Hamiltonian dynamics. I mean, Model C is non-conserved order parameter and conserved energy density. And the usual way you realize this is you treat the energy density as an explicit degree of freedom, but that's the same as if you actually take a microscopic model that has conserved energy density. That's actually, I think, even written in Halperin and Hohenberg.
Okay, thank you very much.
So I think Dr. Basari also made the comment on the, can you make it, can you speak out about the comment if you are still there? Dr. Basari, are you still here or? And in addition, Misha, I saw Misha Stefanov, I saw your hands is up. Are you still want to ask something?
Yeah, if nobody else has questions, I have a couple of questions.
Yeah, please.
So it's maybe even a semantics question. So when you quote Z gamma, I think it's on the previous slide. Does this correspond to any value of the critical exponent in the classification of Hohenberg and Halperin?
No, we didn't. So we didn't find an analogy of this. What we call, I think we call in the paper, we call this relativistic model D or something like this. Of this peculiar version of conserving dynamics without diffusion, so to say, right?
Dynamics without diffusion. How can you have conserving dynamics without diffusion? How does it work?
So the point is, well, I mean, so the point is, so what happens? So let's go to the equation, right? So you have current conservation, right? Your current is your order parameter field plus some spatial current, right? And the spatial current in principle satisfies a relaxation equation, right? Okay. And so let's see what you actually get. So the point is, that if you take the limit gamma to 0, then you actually disable noise. Okay, so you don't have noise. Actually, you don't have coupling to a heat bath, so to say. So you again have a conserved quantity. Yeah, but if you look at just take this, analyze this in mean field, what this corresponds is a mode structure which doesn't have diffusion peaks, but which has this propagating mode peaks. Yeah. So what happens if you change here the,
so gamma is,
then the non-hydro modes moves towards the hydropole, and at the point where they meet, essentially they kind of repel each other and become propagating.
So is gamma inverse of tau r or something like this?
So the way you would usually, we would usually write this when we write them down in the context of hydrodynamics or so, gamma would be inversely, would be, let's see, 1 over tau r, I guess, right? Yeah.
Tau r.
Yeah.
So you are essentially setting tau r to infinity.
I'm setting, yes.
So in other words, it's a sort of Israel Stewart with an infinite relaxation time.
Yes.
I see. And that doesn't correspond to any kind of model and classification of Hohenberg and Halperin.
Yeah.
And it doesn't create any additional symmetry in the system. So maybe
no, it does create. So it does create a conserved. It does create a conserved energy density. I mean, at that point, you basically. I mean, you have some effective Hamiltonian, which has complicated time derivatives, or like which has, I think. I mean, the kinetic term looks different, so to say. Yeah? You have gradients of fields in there as well.
And so related question to this. So model D does not seem to appear in the Hohenberg-Halperin review.
Yeah, so the model D is exactly, so the reason model D
can you say a little more what it is and who decided to call it model D? And maybe you can explain why the letter D is skipped.
I can. The short answer
is always a mystery to me.
Okay.
Nothing between C and E. So.
No, yeah. I can shed further light on this. So usually, when you look at this dynamics of conserved models, you can consider models which have an order parameter field and another density or another conserved density rho. Usually, this is the energy density, right? And usually, the equations they write down is that to the Hamiltonian, these two, I mean, the Hamiltonian can depend on both quantities. Usually there's a coupling between rho and the order parameter, okay? And then both exhibit diffusive dynamics, okay? Now, if you write this down as I wrote it here, this is what's actually called model D, okay, in this literature. Now, the reason it's not in Halperin and Hohenberg is that this coupling doesn't matter, okay? It gives the same dynamics as B, okay? So that's why it was skipped, I believe. Okay.
But why would you skip the letter? Why would no?
I mean, so there. Well, I don't know. I mean, there are a lot of. I mean, there are enough papers who call this model D. Yeah. So when in the book of Teuber or so, it's nicely explained. This is model D, right? Which then goes like I mean. That's like A, B, C, D are, so to say, the conjugate pairs, right? But D just happens to give exactly the same critical exponent as B. Okay, so the coupling doesn't matter, and that's, I guess, why it doesn't appear in the review.
But people already called it D before.
People called it D beforehand already. Yeah.
So, what kind? So the exponents will be in model D are the same then.
Exactly. In the usual model D, you get exactly 4 minus eta also. Yeah. Yeah.
So perhaps we should let Horowitz to ask the last question. Horowitz, it's yours.
Thanks so much. Sorry, coming back to the question I had before about analytics. So, and this is really not my area, so I apologize if this is not a good question, but the spectral function you're thinking about is, I mean, in air quotes, just a 2-point function, right?
Yeah.
And so, and you have a 5-4 theory, so you've got a lambda parameter. So in some sense, could you not do, again, in air quotes, just a tree level calculation of a 2-point function and then be able to compare that with your numerics?
Yeah, you can do that. And I mean, this is essentially, I mean, in the simplest, I mean, okay, if you can do that, and so the brief answer is you can do that in the way from TC this describes the spectral function, right? But then close to TC, I mean, you have this very non-trivial behavior emerging, and you need to do resummations, okay? Yeah, I mean, this is I mean, the way you study this usually, right? The way you study at least the exponents is to renormalization group, right? So you look at, okay, how does this set of modes affect these couplings, right? And you look at, okay, now the next set of modes is affected by these couplings, and you iterate essentially, yeah. Which is telling you need to resum effects basically. That's why it's very hard to get at this, yeah.
Yeah, that's why I was very confused, because normally I think of a classical calculation as just tree level. And that I think of renormalization.
Okay. This was the question that you had. No, so this, I mean, it is like statistical field theory, right? So so classical theory also has fluctuations if you don't consider one configuration, right? But you consider ensembles of configuration. Like in this case, we consider a thermal ensemble, right? Then it's sort of the different realizations of the ensemble that create you the loops, or that create you statistical fluctuations in the system, and that's what loops are, right? Yeah.
I see.
So in fact, you have a very similar I mean, if you were to do diagrammatics, you have a very similar diagrammatics as you would have in a normal quantum field theory. It's just that certain vertices are absent. Basically, you only have thermal fluctuations. You don't have quantum fluctuations. That's the short answer. Yeah.
I see. I see. So then you do your next linear order calculation, and then your couplings run, and that's rather than a quantum correction, it's rather a thermal correction.
Yeah. Exactly. Yeah.
I see. All right. That's great. Thank you.
Hey. Okay. So
maybe I could add. So in principle, if you are looking for analytic, what you are describing is just a comment to William. What you are describing would be correct. This calculation in d equals 4, where fluctuations are not important. And if you want something analytic, I think what you are thinking about is epsilon expansion. Then you can take one loop and resum. And I think such calculations for exponents are described in this Hohenberg and Halperin review. I'm not sure about spectral functions though, but I suspect some spectral functions, or some scaling functions, some scaling functions could also probably be obtained in epsilon expansion, but I'm not sure how much has been done on that front.
I mean, could you not say in principle, do some kind of resummation that leads to some propagator with, shifted masses in particle physics speak, and then use that to get the critical exponents and connect it back then to the spectral functions?
Well, that, as Sören said, requires resummation. That, right? It's essentially a non-perturbative problem in the sense that you cannot just, it requires an optimization group in order to get the exponents and correspondingly the scaling functions. But you can do it when epsilon is small. Then you can you can do it systematically, like in a static critical behavior.
Yeah.
All right.
Okay,
I think thank you all. We already have 30 very active discussions, so I would like to close today's seminar, and thank you, Sören, and thanks for discussion, and see you next time.
Yeah, thanks everybody.
Thank you.
Yeah. Very nice talk. Thank you.
Thank you.
Okay, good.